We're going to be considering the partial differential equation known as the heat equation, which describes how a one-dimensional system, like a heated bar, for example, this can be our bar right here, with some given initial condition of temperature across the bar. For example, we can have something like this as our initial condition, and some condition for the fixed endpoints of the bar, right here and right here, which this, for example, means they're at temperature 0. If we let this height, for example, be temperature, and this length be just position on the bar, it's 0. Let's call this bit over L, this bit over 0, this temperature 0, and this temperature whatever. The heat equation describes in one dimension how the temperature will evolve over time. Now, intuitively, we can imagine that it's going to do something like this, and then it's going to go down to something like this, and it's eventually just going to go down to 0 after a long, long time, right? So what is the heat equation itself, and how do we solve it? So the heat equation looks like this. Del function, del T, is equal to a constant multiple of the second derivative of the function with respect to position, right? How can we interpret this meaning physically? Well, we can see that the sharper this temperature is in compared to the sharper difference the temperature is in compared to its surroundings, the faster that temperature will equilibrate. So if I have a 500-degree point surrounded by a bunch of 10-degree points, well, that 500 degrees is going to dissipate fast. But if I have a bunch of 10-degree points surrounding an 11-degree point, it's not going to be as extreme of a change. So that's how you can interpret this change being proportional to this change. And what's theta here? Theta is an arbitrary function just representing our temperature. The reason I choose theta instead of t is because time and temperature start with the letter t, so only one of them can be t. Okay? So how do we solve a partial differential equation? Well, there are many methods, but the simplest one and the one we're going to use today is the one called separation of variables, in which we assume that our solution theta, which is a multivariable solution of position and temperature, is going to be the product of two functions. One function, which is going to be exclusively a function of x, times another function we'll call big T, exclusively a function of time. Right? And another way we can write this is just big X times big T, because we know based on our amazing letter choice that big X is a function of X and big T is a function of T, where T is time, not temperature. Theta is temperature. Be very careful. So we can write it like this for convenient shorthand. And the reason we do this is because notice we have a del theta del T, and we have a del squared theta del x squared. So we can try and take those derivatives and substitute them into our equation and see if it produces anything useful, which we can then propagate forward and solve. And maybe we'll have some solution to our problem, right? But notice that what's going to happen once we plug this in may change what our equation looks like. Right now it's a partial differential equation, but if you have done this before, you know that it's going to become an ordinary differential equation. It's going to become two ordinary differential equations because we have two unknown functions here to solve. We have to solve for x and we have to solve for t. So without further ado, let's take those partial derivatives and go ahead and plug them in. So the partial derivative of theta with respect to t, this subscript means the partial derivative with respect to t. Let's get this head over here. It's going to be equal to, well, x is only a function of x, so it stays. Big T, however, is a function of t. See, I made a mistake. Time, so we take its derivative. And likewise, theta of subscript xx, which is the second x partial derivative of theta. Well, now x is a function of x, so we take its second derivative. And t is independent of x, so we take no derivatives. And remember, this is why it's useful to have functions that are of only one variable, because we can take these derivatives very, very simply. Now let's plug them back into the equation, and we're going to get that xt prime is equal to k x double prime t. Well, now this looks like something we can separate. In other words, we can have only x's on one side and only t's on the other side. So let's for convenience divide both sides by both sides of the equation by x and both sides by kt. So we're going to end up with something like t prime over kt. is equal to x double prime over x. Now, just because these are both the same symbol, don't get confused. This prime means the big T dt. This prime means the big X dx. Well, d squared big X dx squared. We just use prime for both of them as a convenience, but don't get lost in the notation. So you may ask, why did we divide by k here? Well, in truth, I have some foresight. I know how this problem is going to work out, and it's convenient to divide by k over here. But if you really want, you can keep it over here and see what happens. Nothing bad, it'll just change up the form a little bit, but it should be an equivalent solution. So I have a question now. If I have two functions, one of time and one of position, or just any two functions of two different variables, how is it the case that for every single t and every single x and every combination of both of those at once, that this equality is always true, f of t equals g of x, for any x and t for any f and g? It's simply not true, always. There may be some very small specific case where for one value of t and one value of x that this is true, but the only way that this is true for every x and every t for any f and any g is if f and g are both constant functions. In other words, if f and g are both independent of x and t respectively. So they're just equal to some constant. Right? Now that we got all those words out of the way, what I'm trying to say is that this side and this side can only be equal to each other because this is a function of t and this is a function of x if they're both equal to some other constant. Right? Now I'm going to choose lambda for this constant, and this is going to be a hint that we're probably going to encounter an eigenvalue problem. But again, I have foresight. I'm going to choose this to be negative lambda because it's going to make the problem more convenient. But again, you can explore this on your own and see what happens if you don't. It's just going to be a little bit different notation, and it might be a little bit less convenient for you to work with. But in any case, this is what we're going to go ahead and proceed with. And notice if three things equal to each other, you can pick two of them out and any of that will be true. So t prime over kt is just equal to negative lambda, and x double prime over x just is equal to negative lambda. So we can go ahead and take that out, and we're going to end up with two different ordinary differential equations. Kt is equal to negative lambda, and likewise x double prime over x is equal to negative lambda. Now these are two ordinary differential equations. Remember, this is d big T dt, and this is d squared big X dx squared, right? And these are two ordinary differential equations. Not only are they ordinary, they're both linear constant coefficient homogeneous differential equations if we set up the algebra correctly. But for convenience, let's take a look at this one first. We'll solve this as a separable equation. So if you take a look, we can multiply both sides of that one by k over t is equal to negative k lambda. If you take the integral of this side, you get natural log of t. Always remember your absolute value signs is equal to minus k lambda t. What are we forgetting? Plus c. Never forget your plus c. This is supposed to be a t. Now if we exponentiate both sides, we get absolute value of t is equal to e to the negative k lambda t plus c. Now, word of caution, you can't combine these constants because k is defined by the problem, and lambda is constrained by another equation. So we can't just merge lambda as a arbitrary constant because then we would be changing this equation. We can't do that. However, we can do that with c. Notice that this is equal to e to the c times e to the minus k lambda t, right? And we can also incorporate this absolute value bar into here, and we can say it's plus or minus. But we can take all of this and just call it another constant c naught to get that our equation t as a function of time is going to be equal to some constant times e to the minus k lambda t. All right, so that's one of the two functions we're trying to go for. Now let's go ahead and get the second one. We're going to have x double prime over x is equal to negative lambda. Let's just multiply both sides by x. We get negative lambda x, or x double prime plus lambda x is equal to 0. This is a linear second order constant coefficient homogeneous ordinary differential equation. I love that. So what we're going to do is we're going to write down its characteristic or auxiliary equation, which is going to be m squared plus lambda is equal to 0. And now for all of my fans of eigenvalue problems, because we all love eigenvalue problems, they're so cool, we know that we have three cases. We have the case where lambda is 0. We have the case where lambda, which we're going to set to some arbitrary negative number, let's call it negative alpha squared, is less than 0, obviously. And we have the case where where lambda equal to alpha squared is some positive number. Now, why are we doing alpha squared business? Well, because we're going to have a quadratic here, so it's convenient to take roots that are squares. So if we have a negative lambda, why don't we just make it negative times something squared, which is always positive, so this is always negative, so it's less than 0, and likewise for alpha squared, we'll just have some positive number. That way, when we take the roots, we can just consider alpha instead of having to deal with a square root, and then we could always back substitute later. So this case where lambda equals 0 is going to give us an auxiliary equation that looks like m squared equals 0. So we're going to have two roots that are both m equals 0, 1 and 2. So that means our equation of x, because remember now we're solving this one for x. We're solving this one for x. Our equation for x is going to look like c1 e to the, well, m is 0, so 0x, plus c2, well now this is of multiplicity 2, so we have to add an x here, e to the, again, 0x, which is the same thing as c1 plus c2x. All right, this is a polynomial, so let's go ahead and switch to a different page. Now, if we actually look at our initial conditions, we're going to have that the point over here, this is our boundary condition, that point over here at 0 is held at 0 temperature. And likewise, this point over here at the end of our bar, whatever that may be, is also held at 0 temperature. I'm not specifying units because it's not particularly important to the problem. So let's apply our initial conditions. We know that x of 0 is equal to 0 is equal to c1 plus c2 times 0. Well, this of course means that c1 is equal to 0. So now that we know that c1 is equal to 0, let's apply our second boundary value. Is equal to 0 is equal to c2 times L. Well, if two things multiplied equal to 0, one or both of them have to be 0, but we know that L is non-zero because that's how we defined it, so that means C has to be equal to 0, which means that C1 plus C2x is just 0, which is no good, right? No good, right? So we're not going to proceed with that one. Let's try the case where lambda is equal to minus alpha squared, which is less than 0, right? We're going to get our auxiliary equation m squared minus alpha squared is equal to 0, which means m is equal to plus or minus alpha. So our x is going to look like what? Well, we could say it's equal to c1 e to the alpha x plus c2 e to the minus alpha x, but if we know our cosh and sinh identities, we know that we can write down c1 cosh alpha x plus c2 sinh alpha x, which is sine hyperbolic and cosine hyperbolic, and we know that that's equivalent to a constant multiple of that whole e to the alpha x, e to the minus alpha x business. And if you want as an exercise for yourself, you can go ahead and confirm that. Just be very careful when you're doing it. Keep in mind that we have a free constant. So if something's off by 2 or off by 10 or off by 10 million, we could just, put a C1 there, put a C10 there, who cares? And it resolves it. So we're going to say that x, remember, of x, we don't have to write it. We should write it, but we don't have to right now, is equal to C1 cosh, which is different from the previous C1. We're on a new problem right now. Alpha x plus C2 sinh, favorite sinh, alpha x, right? So let's go ahead and plug in our initial condition x of 0. What are we going to get is equal to C1 times, well, I don't know about you, but I don't know the values of cosh and sinh off the top of my head, but I know what the pictures look like. Love pictures around here. So this one here is cosh, this one here is sinh. So I know that sinh of something times 0 is sinh of 0, and sinh of 0 is 0. So we're just going to get C1 times cosh of some constant. Now, this is 1. We don't need to know that it's 1, because if we know that this is just some value that's not 0, if we have some value that's non-zero is equal to 0, that means C1 over here is equal to 0. So this one goes away. Now if we plug in our boundary condition of XL, which is equal to 0, which is equal to C2 times sinh of, well again, alpha times L is just some constant, so we don't need to worry about it. If we take a look again, one or both of these has to be 0. Let's say we don't want C2 to be 0, right? Because that would mess up our solution. If we take a look at the graph of sinh, unfortunately, well, I drew it poorly. Unfortunately, in fact, let me fix that just so it's not confusing. Unfortunately, the only place that sinh of any number is equal to 0 is at 0, right? Despite how poorly I might have drawn it, that only intersects the x-axis at 0. So this is some non-zero constant, because alpha is non-zero, right? It's less than 0. And L is non-zero, because that's how we defined our boundary condition. This is sine of some non-zero number, sine hyperbolic, which is non-zero. So if this is non-zero and their product is 0, that means unfortunately C2 has to be equal to 0, which means again, no good, right? So we better hope that our last case, right, our last case where lambda is equal to some positive number alpha squared, right? That means m squared plus alpha squared is equal to 0. That means m is equal to plus or minus I alpha. Ooh, complex numbers. We better hope that this gives us a good solution, right? But I have good news. I have good news from the future. It does, but stay with me here. So what are our solutions going to look like? Well, if you recall, our solutions are going to look like C1 cosine of alpha x plus C2 sine. Now these are regular sine, not sin shin cosh, of alpha x. Speed round, let's plug in x of 0. What are we going to get? It's going to be C1, because cos of 0 is 1, plus 0. So that means C1 is equal to 0. This is not good yet if C2 is 0, but let's have hope, right? So this pi 0. Now let's plug in our boundary value. What are we going to get? We're going to get C2 times sine of alpha L. Now we better hope that this is non-zero, so we're just going to try really hard in imagining that sine of alpha L is equal to 0. Now if we know our friendly sine function, your friendly neighborhood sine function, we're going to see that this is true, this equation is true at 0, it's true at pi, it's true at 2 pi, it's in general true at any integer multiple of pi. And in mathematics, we have a way of writing that out. We say that alpha L, for this equation to be true, alpha L has to be n times pi, where n is an integer, right? This little z stands for zinteger. I'm kidding, it stands for integer in another language. So we use it as integers, right? N is an integer. What does that mean? That means alpha is equal to n pi over L. But this is good. We found a value of alpha, which makes our equation true. So in general, not in general, for any specific n, right, we have that x sub n of x is equal to some constant of that particular n times sine of n I x over L. Ooh, we found a solution that's not the zero solution. But trouble, this is not in general a solution to our partial differential equation. Firstly, because we still haven't done our initial condition, right? That's cheating if we just say found it, but we didn't. Second of all, this is only for a particular n, but this is true for every single n. So we have to take that into consideration. Luckily, we recall our superposition theorem, which says that the true x of x is going to be a infinite sum, right? And this should start reminding you of something, right? N equals 1. Of some arbitrary coefficient, let's call it a of n, times sine n pi x over L. This is our x of x. This is a sine Fourier series, a sine-specific Fourier series. Recall that the general Fourier series has a constant term, or a DC offset, if you're familiar with that term, and a cosine term, or infinitely many cosine terms and infinitely many sine terms, but this one in particular only has the sine terms, which means that we're going to have to play with Fourier series, which is good if you love Fourier series. I love Fourier series. So let's go ahead and write out the final fact that we have right here, which is that our big theta over here, let's fix that up. Our big theta is a function of time and position. Well, I said those and wrote those backwards, but position and time is going to be equal to the sum, infinite sum, starting at n equals 1, of some constant depending on n, times sine of n pi over n pi x, let's fix that up, over L, times, let's come back to this for a second, e, some constant. Well, we can incorporate this constant right over here, into this constant, no big deal. E to the k lambda t. Now, on first glance, you might think, okay, let's bring that out of the sum because the sum's only over here. But that's not necessarily the case because we just determined that lambda is dependent on n. So this t is unfortunately also a t sub n, right? So we have to include it in our sum over here. We're going to get e, let's draw that e better. We're going to get e to the minus k. Now what was lambda? Lambda was equal to alpha squared. Alpha is n pi over L, so lambda is n squared pi squared over L squared times t. This is our general, but not including our initial conditions, solution for how our temperature is going to evolve over time of our bar, of our heated bar, or maybe unheated bar, depending on our initial conditions, right? If we set our initial conditions to 0, well, you don't need any of this PDE business to tell you how a unheated bar is going to evolve over time. It's going to stay unheated, right? But let's pick some interesting initial condition, right? Now I'm going to pick the initial condition that theta of x at time 0, so the position, arbitrary position at time 0 is equal to, let's say, 10 degrees of units, whichever ones you want, so long as that number is valid. So we can't do -50 if it's in Kelvin, but that's not our consideration today. So if we just take a look and we plug in 0 for t, we're going to see that this whole exponential term is going to go away to 1. So we're just going to have that this is equal to, this right here is what our initial function is going to be equal to, right? Our initial values. So let's go ahead and take this over here, just like so. So, whoopsie. So if we recall from our friendly Fourier series, we're going to have to solve for these coefficients to represent the constant 10 function as a superposition of different sinusoids of different frequencies of different magnitudes, right? Classic Fourier series. So if we recall, for our case, a of n is going to be the following expression: 2 over L integrated from 0 to L of our function is going to be 10 times sine of n pi x over L. Cool? I think cool. Now, dx, never forget your dx. Now, there's one thing that I'll do to make this problem just a little bit easier. Why don't we set our L to be equal to pi, right? That way, well, this pi is going to cancel, and over here, these pi's are going to cancel. It's just going to make our problem look a little bit nicer. So why don't we go ahead, copy this, and we're going to go ahead and up here, bada bing. So let's go ahead and evaluate for the case that L equals pi, and recall our initial conditions. X at time 0 is equal to 10, right? Doesn't have to be 10. Could be a constant. Doesn't really matter. We also haven't picked a k yet, but you don't really have to. We can pick it later. But you know what? Let's let k equal to 1. Sure. Doesn't really matter. So how are we going to solve this? Well, our general a of n is going to look like 2 over L. Well, we said our L is pi, so 2 over pi. Integral from 0 to pi of 10. Well, let's just bring this 10 out right away. So let's make this 20. Close up that 0. Times sine of n pi x over L, but our L is pi, so just nx dx. Right? The integral of sine, as we know, is cosine, but we have an n over here, so we'll bring out an n. So over pi n. Evaluate this minus cosine x. Evaluate this from pi to 0. Now, cosine of n pi, well, that's going to be something we'll address in a moment, because there is actually a way to express cosine of n pi quite neatly. So we're going to have minus cosine of n pi minus, so plus cosine of 0, just 1, So how do you express cosine of n pi nicely? Well, if we take a look at our beautiful, beautiful cosine function, we're going to get a whoop right there. Notice it's going 1, minus 1, 1, minus 1, 1 at multiples of pi. So this is 0 pi, this is 1 pi, this is 2 pi, and so on, 3 pi. So in general, when it's an even multiple of n, right, 0, 2, 4, right, this is over here, 4 pi, and it's at 1. When it's an even multiple of n, it's going to be 1. When it's an odd multiple of n, it's going to be minus 1. Now, I know a function that does that. It's going to look like this. Pi n. Now, let's just swap the order of these because this minus sign's out front. Not too neat. 1 minus. So what's a function that does this? How about negative 1 to the n? Right? Let's check. If n is even 0, 2, 4, this is going to be negative 1 to an even power. That's just 1. But otherwise, it's going to be negative 1 to an odd power, which is negative 1. So it checks out. It does what we want. Right? So this is going to be our a of n. Now, we're done. If we go ahead and we plug back in our a of n, and we plug in our L, right, we're going to get, and we plug in our k of 1, we're going to get something that looks like our a of n times sine of nx e to the n squared minus n squared t, and the infinite sum of that for however many terms we want. Now, I think that's pretty cool that we're just able to do that by hand, but what I think is even cooler is if we go ahead and we plot the function. I went ahead and I plotted the function in Desmos at different times t. So this one right here is like 0.01 seconds. This one right here is like 0.5 seconds. And it goes on. Actually, this one may be 0.1 second. This one may be 0.5. And it goes on over time. So you can see as time goes, our rod starts off uniformly heated to 10 degrees, but as time goes on, it cools down first from the edges. It cools down slowly, 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 and it's approaching all being an even 0 degrees, exactly as we predicted. But I can do you one better. So welcome to Desmos. Wonderful, wonderful toy here. So you could take a look and see that I've plotted some values right over here, these particular values of our series, which I've only evaluated to 50 terms, right? Because we can get a pretty good approximation of our Fourier series like that. Just take a look at what happens when I put in 0. You see just how our Fourier series is approximating having this straight line at 10 degrees. It's doing so with as many sinusoidal terms as it can, but we're seeing what are called Gibbs phenomena. That's not important right now. What we're going to take a look at instead is a pretty cool little, let's take a look at this. There we go. We're going to instead take a look at what happens in motion, and you can see the temperature of the bar changing over time. See, notice it starts off all the way up there, and it cools down slowly. Right? Let's, in fact, we can make it run slower, not like this, but here, let's make it slower. That's as slow as it'll go. So, see, slowly starts off there, and it cools down over time. Now, this is the solution that we just found analytically, and we're plotting it, and we're seeing like, yeah, it makes sense. Notice that the boundary values are satisfied, the initial condition was satisfied, and it's evolving pretty much how we would expect. If we take a look at the solution over here, we notice that the position over here is determined by a sinusoid, which makes sense, but the evolution over time is determined by an exponential, which again, this also makes sense because the exponential was the solution to the time evolution, but the Fourier series was the solution to the position, right? There we go. Hope this helps. Hope you enjoyed learning about and solving an example for the heat equation. I highly encourage you to pick out a fun little shape for your initial condition and try to solve it yourself. All right, thanks for watching.